Good morning, everyone. Today we are going to deal with the module 1. So, this is module 1 talks about gas power cycle. Heads of this seminar or talk will be a standard cycle. In this, we are discussing about Carnot cycle, Otto cycle, diesel cycle, and dual cycle, and Stirling cycle. So, with respect to this, we are talking about its PV diagram and TS diagram, and description of this cycle, and how to derive the efficiency of each cycle and mean effective pressure. So, once I will explain about Otto cycle and diesel cycle, and dual cycle will be combination of Otto and diesel cycle. So first carefully listen about Otto cycle and diesel cycle derivation. So dual cycle you can do it by your own. Next we are going to comparison between the Otto cycle and diesel cycle. Then we have the gas turbine cycle, that is Brayton cycle. In the Brayton cycle we have several methods for improvement of your efficiency, that is regenerative cycle, intercooling, reheating. So these are the three methods where you are going to improve the efficiency of the cycle. Then finally we are having the jet propulsion system. So this is the syllabus content of this. Next we will deal with the hair standard power cycle. So first of all, whenever you talk about the power cycle, so what it means, the system that produces the power and working fluid goes to the several stages and come back to the initial stage. So that is nothing but your power cycle. And next, refrigeration cycle, where we are going to in a reverse way, where it is taken from the higher region and it is giving back to the lower region. So this is the refrigeration cycle. In the power generation cycle we have two types of cycle, that is gas cycle and vapor power cycle. Gas cycle means we are using some external fuel for generation of the power, whereas in the vapor power cycle we are using the water as a fuel, where it will changes its phase, that is from liquid water into the vapor water. So we have the change the phase in the vapor cycle, whereas in a gas power cycle we don't have any change of the phase, but it will have the high low temperature to high temperature, hence transformation of the power will take place in the gas power cycle. So in the gas cycle, as already we told, that is only one phase will be available in the entire cycle, that is the gaseous phase, whereas in a vapor power cycle we are having the change in the phase, that is liquid phase in the one part of the cyclic process will be converted into the vapor phase for the generation of the power. Hence this vapor phase is very important, hence the name is called as vapor power cycle. In the both the cases we will have the closed cycle, and nothing but it will working fluid will be there in the entire cycle and it will come back to the initial state, and second that working fluid will work on the generation of the power. Whereas in the open power cycle, like IC engine, where the fuel is coming or air is coming and it is given back to the surroundings. So it is not reused. Whereas in a closed cycle, we are reusing the working fluid. So basic consideration while taking the analysis of this power cycle. The cycle encountered in the actual devices are difficult to analyze because of the presence of the friction and the absence of sufficient time for establishment of the equilibrium condition during the cycle. That means whatever actually we are considering, it will be difficult to analyze. So some kind of assumption we are going to make, because in the pipe connecting between different parts of the cycle there will be bending losses will be there, or sometimes frictional losses will be there. So these are the losses we are not going to consider while deriving any kind of equation or when you analyzing any kind of power cycle. So that is the basic one consideration we are going to take. Next, in order to make analytical study or feasible cycle, we have to make idealization, that is neglecting the irreversibility and complexity. That means in the actually process there will be irreversibility available, but in theoretically we are considering the reversible processes. For example, in boiling we are taking that it is process will be taking at constant pressure process, but in actual cases there might be variation in the pressure because of this irreversibility. Hence uh, we are not considering that irreversibility concept over here. So and we are taking assumption such a way that it will resembles the actual cycles. There should not be much deviation when compared to the actual cycles. So these are the cycles. In gas power cycle, what we are talking, a working fluid will be the some fuel which will be in the gaseous phase in the throughout cycle. Example, your petrol engine, diesel engine, gas turbine. So in IC engine, the fuel will be burnt within the boundary of the system, where while conversion of the power, the state or phase, it will have the only vapor phase. Whenever we are considering air is the working fluid, it will goes under several chemical reaction during the combustion, but working fluid will closely resembles this air all the time. Whenever you consider the actual cycles, they are in complex in nature, and so some kind of assumption we are going to make during the air standard cycle. So whenever you talk about air standard power cycle, a working fluid will be the air. So what are the assumptions we are going to make? The working fluid is air which is continuously circulating in a closed loop. So we are considering only closed cycle. We are not considering anything about open cycle. So working fluid will be air and it will be continuously circulating in the closed system. And air behaves as a perfect gas. That means it will obey the perfect gas equation, that is PV equals MRT. So air behaves as a perfect gas and all the processes in the cycle are internally reversible. That means if you change a state 1 to 2, if you reverse that process, it has to come back to the original position. So that is nothing but reversible processes. So all the processes involved in this power cycle, we are considering it as a reversible process. Next assumption what we are going to make is the combustion process is replaced by the heat addition process from the external source. That means we are like the boiler. So fuel is burned outside and that energy will transfer to the water in the boiler. So similar way here also air will be there inside the tube, but for to generation of the power, so fuel will be burned outside and heat is added to the air. So combustion process, it is has been replaced by the heat addition process. Exhaust process is replaced by the heat rejection process, that is exactly reverse of the whatever the combustion heat addition process. Similar way here condenser will be used where heat will be rejected to the surroundings, so that you have to bring back the working fluid to the initial conditions. Next, changes in the kinetic energy and potential energy of the working substrate are very negligible, and we are not considering, since these two parts are we are not taken, because only heat energy or temperature pressure energy is there in the working fluid. So when compared to that energy, your kinetic and potential energy will be very small, and that two energies are neglected while deriving any kind of equations. So these are the assumption we are making in a air standard cycles, and this cycle is known as air standard cycle. So next we are dealing with the Carnot cycle, that is the basic cycle. So whenever you talk about Carnot cycle, so in this we have the two reversible adiabatic process. As you can see, 1 to 2 is the reversible adiabatic process, and 3 to 4 is the reversible adiabatic process, and also it will contain two isothermal processes, so that is 2 to 3 and 4 to 1. So together it is called as Carnot cycle. So corresponding TS diagram is shown over here. 1 to 2, that is the reversible adiabatic process, hence it will be a straight line, and there is no entropy change. So S1 equals S2 equals 0. S2 minus S1 equals 0. Next 2 to 3 will be your isothermal process, that is the constant temperature. T2 equals T3, and 3 to 4 once again it is the reversible adiabatic process, or it is also called as isentropic process, and 4 to 1 is your isothermal process. So 1 to 2 reversible adiabatic process, what will happen? Pressure will increases from P1 to P2, and volume will decreases from V1 to V2, whereas temperature increases from T1 to T2, and your entropy remains constant, that is S2 minus S1 equals 0. So during this process, since it is a reversible adiabatic process, so heat addition to this process will become 0 because entropy is a constant. Next, what about work done? Work done, it is given by P1 V1, that is at the initial state, minus final state P2 V2 divided by gamma minus 1. Now the process, that is 2 to 3, that is isothermal heat addition process. So during this process, pressure is decreases from P to P3, whereas volume is increases from V2 to V3, and temperature remains constant because it is isothermal process, whereas your entropy increases from S2 to S3. So what about the work done during this process? It is given by P2 V2 ln V3 by V2, that is also equal. Since you are considering air as the working fluid, it will obey the perfect gas equation, hence P2 V2 also we can replace by mRT2. So this is the work done equation for the isothermal heat addition process, whereas Q is given by P2 V2 ln V3 by V2. Process, that is the reversible adiabatic process, that is expansion process, that is from 3 to 4. So during this process the pressure will be decreases from P3 to P4 since it is expansion. So volume will be increases from V3 to V4, temperature will decreases from T3 to T4, whereas S will remains constant. That is the difference between S3 minus S4 is 0. Since it is a reversible adiabatic process, value of Q will become 0, whereas work done is given by P3V3 minus P4V4 divided by gamma. Next final process, that is the 4 to 1. 4 to 1 is the isothermal heat rejection process. In this process your pressure is increases from P4 to P1, whereas volume decreases from V4 to V1, and temperature remains constant. Entropy decreases from S4 to S1, and work done, it is given by P4 V4 ln V1 by V4. P4 V4 can replaced by MRT4 ln V1 by V4, and Q4 to 1 it is given by P4 V4 ln V1 by V4. So this is how we will analyze the Carnot cycle. Now we are giving the work done equation for this cycle. So work done will be the whatever area under PV diagram, it will represent the net work done. So already we have noted the equations for individual processes. Now we have to apply that, means for cyclic work done we have to write the equation. So cyclic work done, it is given by work done for 1 to 2 process plus 2 to 3 plus 3 to 4 plus 4 to 1. So all the equation whatever you are written in the earlier slides, now together you have to write. Next, in the all the equation in terms of MRT1, so MR gamma minus 1 is the common, so take it outside from this equation and this equation. So what you will get, T1 minus T2 plus T3 minus T4 and over here the second and fourth term mr is the common, so what you will get t2 ln v3 by v2 plus t4 ln v1 by v4. Next, what you have to do, see here T3 and T4. T3 and T4. Since it is a constant temperature process, T3 also equals T2 and T4 also equals T1. So replace that one and note down the simplified equation, because so T1 minus T2, here T2 will get cancels, T1 gets cancels. So what you will get, mr T2 V3 by V2 plus T1 ln V1 by V4. Just reverse this last term, that is in terms of v4 by v1, right? So what will become, instead of plus it will become minus. What you have to do, now consider the process 1 to 2 and 3 to 4. So we have this, since it is a adiabatic, since it is obeying, air is obeying the perfect gas equation, we know that v3 by v4, that means all the volume terms whatever there in the earlier equation, that has to be replaced in terms of temperature terms. So what you have to do, v3 by v4, that is also given by t4 by t3 to the power 1 by gamma minus 1, but t4 also equals t1 and t3 also equals t2. So replace that term with t1 and t2. Note down this ratio v3 by v4. So hence what you will get, v3 by v4 also equals v2 by v1, because whatever the compression take place, same way expansion also take place. So since the volume ratio will become equal, so v2 by v1 also equals v3 by v4. So or while rearranging the term, what you will get, v4 by v1 also equals v3 by v2. So whatever the earlier equation you add, so replace the term in terms of temperature and simplify that equation, what you will get, work done in a Carnot cycle. So that is nothing but mr ln v3 by v2 into t2 minus equation for the Carnot cycle. Now we have to get the expression for thermal efficiency. So for thermal efficiency, you already in the class we are discussed, efficiency is nothing but output by input. So in terms of, if you want to explain in terms of heat processes, it is given by net heat divided by heat added. So net heat nothing but heat added minus heat rejected divided by heat added. So whatever the heat equation you have discussed in the earlier slide, so that all the heat equation substitute over here. So what you will get, mr will be cancels, so you will get in terms of t2 and volumes. So now once again we have to replace these volumes in terms of temperature. So whatever you are discussed in the last slide, so v3 by v4, that is the volume ratio for the process 3 to 4 and process 1 to 2 will remain same, hence v3 by v4 also equals v2 by v1, or rearrange the term. So what you will get, v4 by v1, that is also equals v3 by v2. So instead of v4 by v1, just substitute v3 by v2 over here. So what you will get, mr is common, ln v3 by v2 also common. So in the numerator, the remaining term will be t2 and t4. So t2 minus t4, mr ln v3. So this will cancels. So what you will get, t2 minus t4 divided by t2, or 1 minus t4 by t2. But t4 also equals t1, hence efficiency will become 1 minus t1 divided by t2, that is lower temperature divided by higher temperature. So this is the expression for efficiency. But in terms of compression ratios. If you want to express this efficiency, so how you can write, so we should know the relationship between temperature and volume. So since it is a perfect gas equation, temperature and volume relation is given by T1 by T2, that is also equals V2 by V1 to the power gamma minus 1. So these relations you have to remember. One is as already told in the class in the module 2 while explaining in the class, already I have told you have to remember three important equation, that is relationship between temperature volume, relationship between pressure and volume, and relationship between volume and temperature for the perfect gas. So you have to remember these three equations. So these three equations you are now you are widely using in this module. So you have to remember temperature volume relation, that is T1 by T2, that is also equals V2 by V1 to the power gamma minus 1, and V1 by V2, that is nothing but your compression ratio, that is denoted by RV. So V2 you bring on the denominator, so what will become V1 by V2, that is replaced by RV. So what you will get, T1 by T2 is nothing but 1 divided by RV to the power gamma minus 1. So substitute over here, so what you will get, thermal efficiency is nothing but 1 minus 1 divided by RV to the power gamma minus 1. So this is the expression for thermal efficiency of the Carnot. Similarly, we have the definition for work ratio. This also already we have discussed in module 2, which is module 3. Vapor power cycle, already we have defined this work ratio. That is nothing but the net work done to the positive work done. Positive work done is nothing but your turbine work in the module 3. Over here also we will get the turbine work. So work ratio is nothing but net work done divided by the positive work done. Net work done is nothing but your usually we are in the module 3 used to told turbine work minus pump work. So here that we have to represent net work done and positive work done. So just rearrange the term and you will get this equation. So just you remember for problem point of view or definition point of view, just this equation, that is work ratio is nothing but net work done divided by the positive work done. Next, we should know what you mean by mean effective pressure. So you just check the in the expansion process, that is a 3 to 4 where your power will be generated. During entire this process, pressure will keeps on changes. So we have to get one average value to identify, because so to solve the problem or to know how much power it is available, so you should know the average value of this pressure. So that is nothing but mean effective pressure. It is the theoretical pressure where we are thinking that is the constant pressure during the expansion process so as to get the power output. So this is nothing but average pressure during the expansion stroke, or theoretical pressure or hypothetical pressure what we are expecting during that process, and we are maintaining that is the constant throughout that volume change process. So this is nothing but mean effective pressure. So usually we are denoted this mean effective pressure by PM, and PS will be the swept volume, and cyclic work done, it is denoted by like this. So as per the definition of a mean effective pressure, it is given by net work done per cycle divided by the stroke volume. Remember, this is the equation for mean effective pressure. So to derive, you should know this formula, that is mean effective pressure is nothing but net work done per cycle divided by the swept volume. Swept volume is nothing but piston from TDC to BDC, how much it will move or how much expansion it will take place. that is nothing but swept volume. In PV diagram, it is represented by from V2 to V4. So how much volume it will crosses, that is nothing but swept volume of the cycle. So next we will move on to the, so Carnot cycle is over. Next we will move on to the Otto cycle, diesel cycle and dual cycle. Next, in Otto cycle, so already we have finished the Carnot cycle. In similar way, we have the Otto cycle. Otto cycle is nothing but your petrol cycle in IC engine. So similar to that, whereas in petrol we are using the petrol as a fuel, but here it is a extended Otto cycle. So we are considering air as a working fluid over here. So in this cycle 1 to 2 it represent PV diagram and TS diagram. 1 to 2 it represent isentropic compression process. 2 to 3 constant volume heat addition. Remember, it is a constant volume heat addition, hence it is a straight line. 2 to 3. Then 3 to 4 isentropic expansion, that is reversible adiabatic expansion. And 4 to 1 is a constant volume heat rejection. Since 1 to 2 is the constant reversible adiabatic process, so in TS diagram it will be a straight line. And 2 to 3 constant volume heat addition, volume will remains constant, temperature keeps on increases. Next 3 to 4 your expansion, that is also reversible adiabatic, hence it is a straight line. 3 to 4 and 4 to 1 is a constant volume heat rejection. So 1 to 2 reversible adiabatic compression, what will happen? Pressure will increases, volume decreases, temperature increases, whereas entropy will remain constant. For this, work done is given by P1 V1 P minus P2 V2 divided by gamma minus 1, whereas Q is 0. That is heat addition to this process will become 0 since it is a reversible adiabatic process. So 2 to 3, that is constant volume heat addition, what will happen? Pressure increases, volume constant, whereas temperature increases, entropy increases. Since it is a constant volume heat addition, your work done will become 0 because PV work will be 0 for a constant volume process, whereas Q is given by, remember, it is a constant volume process, hence we are getting the term CV, that is specified the constant volume, MCV times T3 minus T2. Understood? Next is, that is 3 to 4, that is reversible adiabatic expansion process. So pressure decreases, volume increases, temperature decreases, entropy will remains constant. So Q value will become 0, whereas work done is given by like this. 4 to 1, constant volume heat rejection process. Constant volume heat rejection process. So here pressure decreases, temperature decreases, volume remains constant, entropy decreases from S4 to S1. Since it is a constant volume process, work done is 0, remember. And Q is given by MCV T4 minus T1. So now you have the all the work interaction, heat interaction. Now you have to get the net work done by the. So mean effective pressure. So it is the theoretical pressure acting on the piston surfaces during entire power stroke. Whatever we are taking average pressure, that is nothing but mean effective pressure. So it is given by network done divided by the stroke volume. So network done already we have derived that equation. That is also it is given by our work done for each process. It is given by like this: 2 to 3 and 4 to 1 is 0 because it is a constant volume process, hence it will become 0. Other two already we are discussed. Gamma minus 1 is common, take it outside. So what you will get: P1 V1 minus P2 V2 plus P3 V3 minus P4 V4. So now what you have to do, all these pressure and volume terms, remember in mean effective pressure, all the pressure and volume terms you have to get in terms of temperatures. So long derivation will be there for mean effective pressure. So carefully listen this one, how to convert. So you should know the relationship between pressure and temperature, volume and temperature, and pressure and volume. So PV diagram, keep it in mind how it is there. So we know that for first we will consider that first term, that is P1 V1. So P1 how you can represent in terms of compression ratios. So P2 by P1, it is nothing but V1 by V2 to the power gamma. So this is also nothing but V4 by V3 to the power gamma, that is also equals P3 by V4. So and V1 by V2 is nothing but your RV. So entire term that can be replaced by RV to the power gamma. So what you will get, P2 is nothing but P1 into RV to the power gamma. Similarly, P3 also you will get in terms of RV to the power gamma. But in this over here we will define one term, that is explosion ratio, or other name is pressure ratio. So that is denoted by beta, and it is given by P3 by P2. That is during heat addition process pressure will suddenly increases. So highest in that process the maximum pressure divided by the initial pressure is nothing but a pressure ratio or explosion ratio, and it is given by P3 by P2. So from this equation we will get P3 is nothing but P2 times beta 2, but P2 already this equation, so substitute over here. So what you will get, beta times RV to the power gamma into P1. So P2 is over, P3 is over. Now we have to get P4. So over here already we have P4 is nothing but P3 by RV to the power gamma. P3 value over here it is there. So what will get, substitute and get P4 in terms of beta. So what will get, P4 is nothing but beta times P1. So this is the P4, P3 and P2 in terms of P1 and RV and beta. Next, volume term to convert. So volume. So how to convert this volume terms in terms of RV or in the initial volumes? So clearance volume, you know, this is nothing but clearance volume. So this is the clearance volume, this is the stroke volume or swept volume. So here VC is nothing but clearance volume is nothing but V2 and V3. Since 2 and 3 are constant volume process, V2 become equal V3, that is nothing but clearance volume. And V1 is nothing but Vc plus Vs. So dividing this term by Vc, what you will get, V1 by Vc, that is also equals Vc by Vc plus Vs by Vc. V1 by Vc is nothing but your clearance volume, that is nothing but V1 by V2. So compression ratio RV plus 1 plus Vs by Vc. So rearrange the term. So what you will get, stroke volume in terms of clearance volume and RV value. So clearance volume is nothing but V2 or V3. V2 or V3. So you will get V2 or V3 in terms of Vs divided by RV to the power gamma. RV minus gamma, sorry. Next, V2 and V3 is over. Next, we have to get V1 and V4 in terms of stroke volume. So we know that compression ratio nothing but RV is nothing but V1 divided by V2. So from this equation, you will get V1 is nothing but V2 times RV. So V2, whatever the value you got, substitute over here. So you will get, since V1 is equal to V4, so whatever value you got V1, same value for V4. So this is the expression you will get for each volume terms V1, V2, V3, V4. So now pressure term you got, volume term you got. So these two terms, to all the pressure and all the volume terms, you have to substitute it back in the initial mean effective pressure. So one big equation you will get, that is the initial work done equation, 1 by gamma minus 1. This is the initial work done equation. Substitute all the p terms and v terms. So you will get this big equation. So in this equation, just try to take the common terms outside and get the reduced equation. See step by step, here it is explained. Gamma minus 1 was there, so RV minus 1, so it will be common in all the four parameters, so four terms, so that is taken outside. P1 is common, Vs is common, and RV is common. So this is the common term taken outside. So here it will become 1, then minus, here it will become RV taken outside, so RV gamma minus 1 plus third term will be, here beta is not common, RV taken outside, so RV gamma minus 1 and minus once again here it is beta. So rearrange the term, so what you will get, so this will be as it is. Next, inside the bracket, what you have to do, 1 minus beta or beta minus 1, whatever it might be, here two term will be the second and third term. So here RV to the power gamma minus 1 is common, so beta minus 1 you will get taken minus outside, so beta minus 1, again beta minus 1 you can take it outside. So what you will get, final expression for net work done, final expression for net work done you will get like this. So now for mean effective pressure, what is the equation, that is net work done divided by stroke volume. So net work done equation you got like this, divided by Vs. So what you will get, just Vs will get cancels, so you will get mean effective pressure is like this. Pm is nothing but 1 divided by gamma minus 1 into Rv minus 1 into P1 Rv beta minus 1 Rv to the power gamma minus 1. So this is the expression you will get for mean effective pressure. So this derivation is important. Practice it once again, whatever the explanation what we have given. So practice it one more time, you go through it and practice it. So today will be till here I will finish. Tomorrow we will go for diesel cycle and dual cycle.